And it was Arthur Compton who successfully proved that Einstein's suggestion of the linear momentum was really correct. Okay, so it was basically how he performed this experiment. He used the X-ray beam because X-ray had a high enough energy to eject photoelectrons, and he sent it, he sent the X-ray of a certain wavelength lambda into a metal target which has a lot of electrons. And after the light is X-ray is scattered, he measured the frequency or wavelength of this scattered X-ray as a function of scattering angle. Okay, so this is basically the result he obtained. Okay, at 0 angles, for example, if you have a detector here, he was of course measuring the wavelengths which he originally used, which was more like 71, right? Okay, and then if you go to 45 degrees here, you will still see the signal at 41 picometer here, and then there is a broad, another pig-like structure at a little bit right side, which is a larger wavelength. And then if you go to 90 degrees, for example, if you have a detector here, then the peak at 71 is still there, and then you can see there is clearly another big peak at higher wavelengths, probably around 73. Okay, so we can say this is maybe about 72, right? Okay, and then if you go to 135, for example, if you have a detector here, then you still see the peak at 71, and then the second peak appears at 75. You can see that as you go to higher angle, the wavelength was continuously changing to higher wavelengths. Okay, so how did Compton explain this? He basically used the idea of the conservation of energy and conservation of momentum and tried to explain it. Here, in these calculations, you do not need to know the details, because in order to understand these relations, you actually need to know the relativity. For example, this gamma actually comes from the relativity. So therefore, don't try to understand the details, but basically idea is that it was performing the collision experiment between the X-ray and the electron, and exactly following the scheme of the elastic scattering that we have learned the spring semester. And of course, important thing to remember is that for the energy of the X-ray, he used the quantum of the energy suggested by the Max Planck, HF, and for the linear momentum, of course, he used the linear momentum suggested by Einstein, which was Planck constant divided by the wavelengths. And he finally successfully explained that the wavelengths after scattering actually depends on the angle. So he was correct, and indeed this experiment proved that Einstein's linear momentum idea was correct. So therefore, now we know light quanta, which we call photon, has a linear momentum even though it does not have mass. Okay. And in this slide, we are going to discuss something very strange. Okay. Now let me ask you a question. If light wave has a linear momentum like particles, then would the particles of electrons or matter behave like waves too? Actually, the person or scientist who had this question first was Louis de Broglie in 1924. So he assumed that this is correct, and he hypothesized that the momentum relation for photon also applies to electrons. Okay, what is the momentum relation for photon? This was Einstein's momentum relation, Planck constant divided by the wavelengths. So if you rewrite this, now you can write that the wavelengths must be Planck constant divided by the linear momentum. And if you have a particle which has a mass, now you can write this momentum to be mass multiplied by the velocity. Okay, so this is a very strange idea because the matter like electrons are actually waves. So this is what we call matter waves. So matters are waves. And then, is it really correct? Of course, if this is a wave, then it has to undergo interference and diffraction like we learned before. So indeed, just 3 years later, Davidson and Germer experimentally proved that electrons undergo diffraction and interference like waves. Okay, so for example, if you accelerate electrons using the potential and then let them go through this double slit, and then this is the pattern you're going to observe, just like Young's double slit experiment, but now this time using electrons. So it actually proves that electrons are waves, which we call matter waves. Okay, so what does it actually mean that electrons are waves? Does it mean that electrons are moving like this when it's moving forward? Actually, it doesn't. It does not mean that electrons are moving sideways, like forming this type of wiggly pattern. What it actually means is that the existence of electron itself is represented by the probability amplitude function, and the square of this amplitude is actually the probability, which means that electrons do exist in space and time. Remember, when we dealt with the light, the amplitude was actually the changing electric field, and if you take the square of this amplitude, you got the intensity, and intensity is what we actually measure in light, the strength of the light, right? Just like that. Now the wave of this electron, we will use the sine function to represent the matter waves of the electrons, sine functions or cosine functions, and that is called the probability amplitude, because you have to take the square to get the real probability. Okay, so this is the idea of the matter wave. And so therefore, because now electrons work like waves, the electrons that we observe as particles are no more than the constructive interference between these electrons' probability wave function. Okay, so it may sound a little bit strange, and just like that, quantum physics is a very strange phenomena which is very difficult to understand if you simply think about classical physics. Okay, so we will continue to discuss the quantum physics, especially the matter waves. So how do we use mathematics to describe these matter waves, which are matter and waves at the same time? You know, essentially they are waves. So therefore, they have to satisfy the wave equation that we have learned in the spring semester, particularly in chapter 16. You know, in this wave equation, the second partial derivative with respect to time must be equal to the second derivative with respect to the position, and they were related by the square of the velocity. And of course, this velocity was actually the angular frequency divided by the wave number. Okay, and then these are the definitions of the angular frequency and the wave number. And then we learned that the simplest solution to this wave equation could be written using the cosine function or sine function. And you can see these two represent traveling waves, because this k and omega, from this k and omega, you can get the velocity, which is of course omega divided by k. Okay, so then actually following the simple mathematics, you can combine this cosine function and sine function by using this complex I. You can make them actually exponential. I think probably you don't know about this, but probably if this is the first time you have seen this, it will be a good idea to remember it. Exponential of I theta is equal to cosine theta plus I sine theta, because this is a very famous equation in mathematics, and probably you will see these many times in many different areas. Okay, so I strongly recommend you to remember this. So therefore, we can actually represent the solution either using cosine sine or even using exponential function. And when you use exponential, actually most of the time it will contain this complex I. Okay, so basically the idea is that we will represent the solution of this matter wave equation using this type of formula, and then we will call it wave function. Okay, these are the functions that represent waves. Okay, and then of course in 3 dimension, they can be, the variables can be x, y, z, and also time. And actually you can separate out the time. So why does it look like this? Actually this term is exponential, so therefore you can separate it between exponential of I kx multiplied by exponential of minus I omega t, right? So therefore you are actually separating out this term. So therefore it contains this complex I. So remember that these wave functions are actually complex functions. So they are different from the real function we typically use. They are complex numbers. This is the very strange property of the quantum physics. We are dealing with complex functions. And for the spatial part, okay, this is what we are more interested. Actually dealing with the time term is a lot more difficult, and we are not going to study that in this chapter. So we are only going to think about this spatial term, and of course for simplicity we will discuss the 1 dimension first. Okay, and then the simplest way to represent this function will be simple linear combination between cosine kx and sine kx, or linear combination between exponential I kx and exponential minus I kx. If you properly combine these two, you can recover cosine and sine. Okay, so probably I will leave as your homework, what is the relation between these constants a, b, and c, d. Okay, and then finally they can represent some wave-like functions like this. Okay, so this is what we call wave function, and in the previous slide we said that they represent probability amplitude function. So therefore, in order to get the real probability, what you have to do is you have to take the square. And remember, phi, now in this case, is a complex function. So therefore, you cannot directly take the square, because if you take the square of the complex number, it may again become a complex number. And the probability must be a real number. So how do you get the real number from the complex number? You actually have to multiply the complex number by its complex conjugate, right? Okay, that's what we are doing, and it's just like this. If you are multiplying a plus ib with its conjugate a minus ib, we write that this is actually the absolute square like this, and then what you get is simply a square plus b square, which must be larger than 0 or equal to 0. It cannot be smaller than 0. So this is how we take the square to get the probability density, and then this probability density represents the actual existence, probability of the existence of the electrons. So therefore you can actually integrate this function over a certain area. For example, the value you get will represent the probability of electrons to exist within this range. Okay, this is how you calculate. And one more thing, of course, this probability density function is essentially a probability. I think you have learned from high school that the total probability must be 1, right? The probability of anything cannot be larger than 1. So therefore, if you integrate this function from minus infinity to plus infinity, that will be the probability of finding this electron anywhere along this position, along this axis. So therefore, that must be equal to 1. This is called the normalization condition, because it allows you to find the value of the constant given here. Okay.